Good afternoon, everyone. My name is Nikita Shamgunov, and I'm the CTO of MemSQL. And today we're going to talk about PowerStream, propelling energy innovation with predictive analytics. Some of the topics that we're going to discuss today: the on-demand economy, from in-memory computing to in-memory databases. We're going to understand what the differences are and which technology is useful for what. Then we're going to talk about renewable energy and how PowerStream allows you to process a lot of IoT, Internet of Things data. And then we'll demonstrate PowerStream, which we built on top of MemSQL and on top of real-time data pipelines, processing very large volumes of data. So there is no question that we live in the on-demand economy today. And customers are conditioned through consumer applications such as Uber, such as Stripe or Airbnb, to kind of instant gratification and instant access to services. But where does it leave enterprises? So enterprises are racing to meet internal and external expectations for speed and personalization. And the reason to that is their customers and their employees are conditioned by all those consumer apps and to have real-time access to pretty much any service out there. So what blocks the enterprises? The real enemy to real-time is batch processing. And batch processing is what forces enterprises to perform computing overnight. What they need to do is to shift into real-time data processing and intraday operations. So it all starts with data generation. And this is a very, very typical architecture for MemSQL customers that start with consuming data generated by mobile devices, generated by IoT, by sensors, by API requests. And once they harvest all that data, they need to put it somewhere. If you want to process it in real time, a typical destination is Kafka. So we have a lot of real-time inputs, could be API requests, data is in Kafka, and then we provide an application called Streamliner that's built on top of Apache Spark that lets you consume data from Kafka in microbatching, perform and apply different transformations, and later on, we're going to talk about some of the cool transformations with predictive modeling that you can apply, and then put that data into MemSQL. So MemSQL is an in-memory database. So once the data is an in-memory database, you get the full power of the ability to attach a BI tool to the database, the ability to build a transactional applications, the ability to generate reports, the ability to insert, update, delete, and manage the system of record of that data. So here's a few examples. One of our customers, Comcast, is achieving sub-100 microsecond latencies for powering their mobile applications. The pipeline looks extremely similar to what we saw in the previous slide. Data comes from Xfinity X boxes that a lot of people have in their houses. They're consumed by Flume in this particular case, not Kafka, but nonetheless, they process the data in Storm and push it into MemSQL at the rate of 300 events per second. And that enables them various real-time analytics capabilities, from diagnosing issues in real time, proactive monitoring, but also building real-time applications such as powering mobile Comcast applications, as well as enabling real-time recording. Here's another example, which is in a way similar but in a way different. MemSQL runs at Pinterest and processes 75 terabytes of data a day. And with a very standard architecture where pins and repins come from a mobile phone, they store them in Kafka, pull that data from using Spark, enhance it, and in fact, they do reverse IP lookup and enhance it with kind of geography region for each IP address, and store it in MemSQL. 75 terabytes of data a day is about 1 gigabyte a second. So they're storing kind of the full movie, I would say, a second in MemSQL in API requests. That data is available immediately for the analyst inside Pinterest. And that's how they know the performance of their ad campaigns. That's how they know, the efficiency of the code they just updated because they have continuous delivery of the code in their applications and the website, and so on and so forth. So what is an in-memory database? As you can see, an in-memory database can power this really, really large-scale applications with large volumes and large velocities of data. So we're going to spend a bit of time understanding what an in-memory database is and what in-memory database is not. So what do you think? An in-memory database, does it use memory instead of disk? Who do you think, is it a true statement or not? Some people think it's a true statement. Not necessarily. Another question, does in-memory database does it need to save data on disk? Yes or no? Yes. OK. Well, it actually does need to store data on disk to enable transactional semantics. Does the in-memory database need to put the whole data set into memory? OK, no, it does not have to. So sometimes it does, sometimes it doesn't. And in the case of MemSQL, we support different table types. And some table types have to store the whole data set in memory. And some table types do not. So Wikipedia says that an in-memory database primarily rely on main memory for storage. What does it mean primarily? It means that it gives the user that flexibility to pin certain data sets into memory to enable faster processing, to enable guaranteed SLAs for their lookups. In the case of Comcast, we do sub-100 millisecond lookups. But it does not have to put all the data in memory, and it does not mean that if you pull the power code, you lose all your data. So in-memory databases are actually durable to disk. And certainly MemSQL is durable to disk. It supports ACID, atomicity, consistency, isolation, and durability. In-memory database can actually spill on disk. What does it mean, spill on disk? If you put more data than there is into a database than there's memory in the system, they will put as much as they can into memory, but then the rest will be spilled on disk. The other case when spill on disk is necessary is when you do query processing. So if you have a large cardinality group by, or you perform a large join, you need more memory to process that data than you have in the system. And in this case, you will start spilling that data on disk. But in fact, the in-memory databases are designed for the world that has a lot of memory. Right? And this world is kind of in front of us. Memory is getting cheaper and cheaper. You can go on AWS and start getting machines with terabytes of RAM now. Despite the fact that everybody is saying that memory is getting cheaper and cheaper, it's still pretty rare to have access to machines with terabytes of RAM. So for example, my laptop only has 16 gigabytes of RAM. I would love it to have 32, but I cannot buy a Mac with 32 gigs of RAM. So that's why in-memory databases tend to be distributed systems. And the reason to that is you will be able to have a cluster of machines that will give you, the amount of RAM on one machine multiplied by the number of nodes in the cluster. In-memory databases have different set of bottlenecks than traditional relational databases. And we'll talk about it a little bit more in the future. So I'm going to make a bold claim now. You ready? I want to say that all database workloads will be running on in-memory databases in the future. So why am I making this bold claim? So yes, memory is getting cheaper.
That's one. And cache is kind of a new RAM. So RAM is the new disk, and disk is the new tape, and et cetera. And the other thing is that in-memory databases leverage SSDs for for no random writes. And that means that with a combination of RAM and SSD, you'll be able to surface pretty much any database workload. And the final point, that NVRAM is coming. And NVRAM stands for non-volatile RAM. I believe Intel promises this NVRAM to come to market early 2017 in various form factors. One form factor is going to be a hard drive. Another form factor is going to be actual RAM. And it's a non-volatile RAM. And going forward, we may live in a world where it's actually cheaper than an SSD. So it's a revolutionary technology that's coming into market. It's going to be, when it comes to market, it's going to be 3 times as slow as RAM, but persistent, and twice as cheap. So now that we talked about in-memory database, let's shift gears a little bit and talk about renewable energy. So some of the things that are in the news, right? Denmark is aiming for 50% renewable energy source within the next few years. You continue, like if you just start Googling renewable energy, you will see that Portugal, which is not the richest country in the world, but 22% of the electricity in Portugal is provided by wind farms. So this is kind of massive. So we're living right now, and this massive shift in energy production and consumption is happening. And Germany just got almost all of its power from a renewable energy. And this is really, really big, because Germany is a very industrialized country. So now we're going to talk about PowerStream. So what is PowerStream? PowerStream is an application that's built according to the architecture we described earlier in the presentation. And PowerStream is predicting the global health of wind turbines. So there are about 200,000 wind turbines around the world. A lot of them are in the United States. A lot of them are in Europe. And then also there's more and more coming up in Asia and other continents. So imagine the world where each turbine sends their status, sends their updates about how the turbine is doing, sends their telemetry out there. And what if we had a system that could consume all that telemetry at the scale of 200,000 turbines, sending multiple requests a second and reporting about its status? Well, that system is MemSQL PowerStream. It runs on a relatively modest cluster, and I'm going to show you this cluster right now. It's only 7 machines. Those are AWS C4 2x large instances. It costs 30 cents per hour per machine, so the annual cost is $20,000. But the cool thing about it is that it allows you to consume millions of events per second. And not only that, it allows you to do very sophisticated things with that data that it captures. So let's look at the Streamliner architecture for PowerStream. So data is produced by sensors. And like I mentioned before, the natural way, once you get all this data, once you collect all this data, is to push that data into Kafka. So now when the data is in Kafka, and by the way, who knows what Kafka is? OK, a lot of people know what Kafka is. That's great. For those who don't, Kafka is a persistent message queue, which is also distributed. So it allows you to push data into a message queue at a very high rate. And since it's persistent, you do not have to immediately consume it. It can sit there, in certain cases for like days or weeks. Or if you're consuming that data quickly, you'll be able to push data processing into pretty much real time, and not even pretty much, into real time. The power of Kafka is is because it's distributed, and it's also persistent. So if the consumer is down for whatever reason, or if some of the producers is down, it still maintains that state for some time. So once it's in Kafka, and Kafka is very, very simple, it's just a message queue, we give, MemSQL provides this application called Streamliner. It's part of the any MemSQL installation, where you can just paste the Kafka URL into the system. And it will start consuming that data and push it into a MemSQL table in cases at enormous rates. Streamliner is built on top of Apache Spark, so we use Spark streaming. And you can also inject code into the Streamliner built against Spark interfaces. So how many people know what Spark is? Very cool. Yeah, so Spark is kind of general purpose cluster compute technology, and it allows you to consume data from streaming data sets using Spark streaming. Now, from there, the data is pushed into MemSQL. And as it pushed into MemSQL, we actually maintain the state of each turbine. So there's a table that has all the turbines persisted into MemSQL, and every time we receive more telemetry, we go and update the state. So we make decisions in real time as we process all that data, and we go and say, oh, okay, this turbine is down, or this turbine is about to be down, and whatnot. So we can derive a lot out of that data that's streaming into the system, and we can persist it. And then PowerStream is the user interface, is an application built on top of MemSQL. It provides you a graphical UI, and you can see and monitor what's happening with each individual turbine. So it gives you that power and instant access and instant knowledge if certain things are down or unhealthy, you want to issue some maintenance and whatnot. So that's a screenshot of PowerStream, and I'll be showing you PowerStream live as well. Here it says 1 million writes a second and 200K reads a second, and this amount of kind of query volume, I would say, is necessary once you deal with such large and high velocity of data. All right. So let's go and take a look at PowerStream right now. I'm going to switch to my Chrome. OK, so this is PowerStream Live. I'm going to refresh this page to make sure everything goes well. So at the moment, we're processing close to 1 million updates a second. And each turbine here is sending those Internet of Things type data. So what I'm going to do now, I'm going to explore the globe. Let's just take a look at the application and find out which continent or which region has the most turbines in the world. Okay, so I'm going to zoom out a little bit. You can see there are a lot of turbines in the United States, not as many in Canada. But let's go to Europe. As you can see, Africa is pretty much turbine-free. But when you go to Europe, you'll see that Europe is all covered by wind turbines. And there's nothing in Russia and Ukraine. Like there's just emptiness. But as you go to Asia, you'll start seeing more. And there are a lot of turbines in Japan. The other thing that I'm going to do, I'm going to run a few simulations that will kind of trigger some activity in these events that turbines are sending. So let's go to my controller. And you can say, let's say, agent infrastructure in Germany. So we're going to go back. And what we're going to start seeing is all these red dots here in Germany. So, the cool thing is we can start zooming in And each square here is not one turbine, is one farm. As we get closer, we can go down, and now we see individual wind turbines. So the granularity of this, kind of the resolution of data that we have, is per individual wind turbine. And we captured all of them in the world, each one of them sending a ton of data each second. And since we are running our simulation of aging infrastructure in Germany, we're starting to see how certain turbines are going out of commission. We see more and more of that. OK, so let's look at the cluster. The cluster that powers data processing for this application is a MemSQL cluster that is currently running on Amazon AWS. And here are all the nodes. And like I promised, there are about 7 nodes. There are 7 nodes in this cluster. All the IP addresses are internal IP addresses from Amazon. This is the CPU utilization for every node in the cluster. So we're about kind of at 50% capacity when it comes to data processing. So let's see how we actually process that data and look at the Streamliner application. So in the Streamliner, we have 2 data streams. One is sensors, and the other one is alerts. I can click on sensors. And we can see that we're pushing about 1.5 million rows a second. Data is coming from Kafka. This is the Kafka connection. It's just the IP address and a port. The topic is data points. And then we also have a user-defined transform. So what is a transform? If you guys have worked with Kafka before, you understand that Kafka is unstructured. So every message in Kafka is just a bag of bytes or a blob. And we need to kind of interpret what data we're having in Kafka. So for that, Streamliner allows you to upload your jar, written in Scala or Java. And within that jar, you need to define how you interpret those bits that you're pulling off the wire in Kafka. So in this particular case, this is just the class name inside of that jar. And when you create a new pipeline like this, for example, you specify a Kafka URL here. And here in a transform, you can either say, I want to emit it as a JSON column, or I can emit it as a CSV, or I can provide custom Scala or custom Python. And if it's custom Python, you can just type your transform right here. So it's incredibly straightforward, incredibly easy to go ahead and define your data processing pipelines. And those pipelines will be just persisting that data in MemSQL and run some user-defined code as part of that process. Then you need to specify where you load it to, which is a database and a table name. Once you click Save, that's it. Your pipeline is defined, and you can start processing data at insane, like ludicrous speeds. Cool. So let's talk about predictive analytics. So obviously, it's very cool that we can process and capture all that data in real time. You don't need a ton of hardware to do so. And we can very efficiently store it inside MemSQL, either in memory if you want to have access to an individual data point inside MemSQL, or you can store it in MemSQL column stores for archiving purposes, and then store incredibly large volumes data in MemSQL column stores, which are on disk. But one thing is to store it, and the other thing is to really act on that data in real time. So acting on the data in real time is basically predictive analytics. So if you want to predict which turbines are going to go out of commissions, instead of knowing which turbines already went out of commission, that's a real power, right? Because every time something fails or something goes wrong or breaks,
you're losing all that time, and because of that, you're losing all that value that this piece of infrastructure delivers on. And a lot of our customers using predictive analytics as part of the Streamliner pipelines. You can do it in a multitude of ways. And some customers are kind of entrenched into SaaS models. They use SaaS, which is a decades-old analytic software. They build those models in SaaS. They have a big workforce that is trained to produce those models. And then you can export those models in PMML, which is just an XML serialization of the model. Once you have that, you can send this PMML into a MemSQL transform. And as a part of storing data, as a part of the pipeline, MemSQL will be able to apply that model to every incoming data point that goes into MemSQL. And not only you will be able to store all the raw data in MemSQL, you'll be able to store predicted values right there as part of, as a column, for example, in a MemSQL table. And then an application that's built on top can read that and understand which turbines are going to go out of commission sometime soon, maybe in the next few days. And since it has a tight integration with Spark and tight integration with Scala, which has a ton of libraries, you can either import your models produced in SaaS, or you can create those models on the same data that you already have using Spark MLlib. So that allows you to do predictive scoring as part of creating the pipeline. So we're going to be transitioning to a Q&A. But before we do that, I want to encourage everybody to stop by a MemSQL booth and pick up this book. It's an O'Reilly book that tells you how to build real-time data pipelines. Of course, at the MemSQL booth, you can grab a MemSQL t-shirt. We have a brand new logo. It's awesome. So don't hesitate and get a t-shirt there. And thank you so much, and we're transitioning to Q&A. Go ahead.
All that data from those wind turbines, is it like an open availability? You tap into a business stream from around the world that all different companies provide the data of their turbines?
So there are several pieces of data, right? So one is the location of every turbine, and that data is public, or at least you can purchase that. Then you can purchase wind turbine data. But that is obviously a highly confidential and sensitive data, and it's not public. So what we did, we purchased all the turbine locations, and we purchased samples of that data. And the rest of it, we built a simulation on it. So that's what I'm demonstrating to you right now.
Okay.
Good. Correct. This is a very good question. Let me repeat the question. So MemSQL is an operational in-memory database, and how is it different from VaultDB? So there is a number of differences between MemSQL and VaultDB. One of the biggest difference is MemSQL allows you to run ad hoc queries, and it has very, very strong query processing. So for example, it supports all types of joins, all types of subselects. It allows you to join data that is not necessarily sharded the same way, which is not the case in VaultDB. It supports geospatial indexing, so you can build geospatial applications. And it also supports column stores. So you don't have to store everything pinned in memory, but you can also have kind of historical data to enable certain data warehousing scenarios, for example. So the short answer is, even though MemSQL and VaultDB look similar on the surface, MemSQL has basically way more features to be a kind of general purpose cluster database. Go ahead.
What any bottlenecks do you run into in terms of ingestion? Do you run into a lot in what areas?
Yeah. So this is a very good question. The question is, what are the bottlenecks on ingestion that you're running into?
It's a lot of data, right?
So this is a lot of data. So there are multiple potential bottlenecks. So let's talk about them. On the system level, there's obviously CPU, network, and disk. All right, and MemSQL persists all that data on disk on every node, even though it's an in-memory database. There is a reason that MemSQL here runs on 7 nodes, not on 1 node, because obviously on 1 node we wouldn't be able to scale it to this level. So CPU is obviously one, because every time you ingest this data, if you want to update the state of each turbine efficiently, you need to create some sort of index on the table of all the turbines. And
It's a real-time index.
it is a real-time index, absolutely. And for every data point that comes in, you need to navigate through that index, find the record, and update the state of the turbine. So because we partitioned that on 7 nodes, we're processing 1 million divided by, or actually 6, by 6, so 150,000 updates per second per node. So, and this is CPU bound. It's surprisingly, it's CPU bound, not IO bound. And it's not IO bound because we only do sequential writes. The other bottleneck is just the ability for Kafka to push this much data through. And in fact, there's a sizable Kafka cluster here as well. So you cannot push all the data through just one node in Kafka. So there's another one. And then once MemSQL knows how to push this much data, and Kafka knows how to push this much data, the process of pulling that data from Kafka and persisting into MemSQL is yet another bottleneck. So how fast Kafka can return that value into an external client, and how much network is between the two clusters, and do the clusters allow you to pull that data in parallel?
Kafka is limited by what?
Kafka is limited by the same stuff, right? So, CPU, I/O, and network, right? So we had to build the system that allows you to pull from Kafka in parallel. So it does not have any bottleneck, and communication between Kafka and MemSQL is a cluster-to-cluster communication.
So do you have any issues with data getting out of order when you're ingesting data from so many turbines?
Mm-hmm.
So how do you
Yeah, very good question. So in this particular application, no. In general, yes. So when data goes, yeah, absolutely. Do you have any issues with data coming out of order? So from Kafka into MemSQL, or from any other streaming data set into MemSQL. So for those who are familiar with Kafka, Kafka has the notion of partitions. And the order is only guaranteed within a partition, right? And you cannot have order guarantees across partitions. The good thing is that MemSQL supports indexes. And whatever order you need to have, for example, you want to enforce order on the timestamp, or you want to enforce an order on user ID or whatever identity you might have, you can create an index on that. And if you have an index on that, MemSQL will sort it for you. And it's actually very, very efficient in sorting. And it supports sorting for both row stores and column stores as well. Over there in the back. Say again? Yeah. The question is the data 100% persistent? And the answer is yes, absolutely. So everything that you store in MemSQL is immediately available and persisted.
Do you have any multi-data center replication storage?
The question is, do you have any multi-data center replication stories? The answer to that is yes. We have multi-data center replication story. The API to that is very, very simple. Let's say you have 2 clusters. One is East Coast, one is West Coast. Let's say on the East Coast, you already have a cluster running. You spun up another cluster on the West Coast. The only command you run on the West Coast is replicate database from and specify IP, connection credentials, and database name. You press enter, and from that point on, we'll pull all the data into the slave, and the slave will eventually catch up. So we do it by shipping transaction logs on the other end. Now, the only limitation to that architecture is this is a master-slave replication, and the slaves are readable, but they're not writable. And if you want to write into a slave, you need to basically break that replication.
So it's basically active-passive.
Active-passive, or master-slave, yeah. The question is, what is the future roadmap to MemSQL? So the future roadmap to MemSQL is to make every company a real-time enterprise. So we strongly believe that data processing is moving into real time, and everybody is going to have real-time applications. So we build the best in the world database technology to enable every company to be a real-time enterprise. So that's on the high level. On the lower level, we're investing into clustering. We're investing into query. We always invest into query processing. So we want to be, for every database workload, particularly distributed database workload, particularly real-time database workload, we want to be the best in the world technology. And so we always invest into query optimization and query execution. And if you kind of drop down from there, we are investing into vectorized execution, leveraging modern hardware, things like SIMD for faster evaluation of queries. We're investing into distributed joins, and those who are familiar with data warehousing know that in the distributed systems, there are a lot of data reshuffling that's happening as part of the evaluation of the query. So we're investing into making this more efficient. We already have that, but there's always new research that comes in, and we're part of it. We are going to every major database conference, and we're taking all that knowledge and technology and putting it into the product so our customers can build more efficient real-time applications. So Vertica is a data warehouse, and MemSQL is a database. So you can build real database applications on top of MemSQL, and with Vertica, most of the applications are BI tools that you attach to Vertica. So you cannot build, real-time DVR, like something that Comcast built against Vertica. Now, if you go and just look at the data warehousing part, we're pretty much on par or better for just the data warehousing part with Vertica. We're just as fast or faster. We ingest data faster. We support column stores, so kind of the underlying data format is similar to Vertica, but it's more modern because we're a newer technology. And where we're going is that every workload that can be captured by Vertica soon will be captured by MemSQL as well. What we don't have, and I want to be upfront about that too, is we don't have R integration, for example. And that's something you can do with Vertica you cannot do with MemSQL yet. But the pace of innovation and the speed at which technology evolves, again, we'll be able to capture every Vertica workload very, very soon. There's another question back. Andy.
How do you compare this to SAP HANA?
So HANA is an interesting story. They say that it's distributed, but it's mostly a scale-up system. And MemSQL is a scale-out system, and it scales out on commodity hardware. HANA also is a combination of like 8 different technologies kind of lumped together. And MemSQL is built from ground up. That's kind of on the high level. The purpose of MemSQL is in a way similar to the purpose of SAP HANA. We want to make every database application real time. We want to make every database application faster. We want to make every application to be able to run what is called hybrid transactional and analytical workloads, being able to efficiently generate reports and run analytical/data warehousing queries, as well as process transactions. Go ahead.
Maybe you have to thank SAP to prove your point that every database will be in memory. Because SAP always said, our big SAP system is now only on HANA. So it actually proves your point.
The question is, should we say thank SAP for promoting the new type of applications and promoting the new type of technologies? And I would say yes. Thank you, SAP. But MemSQL is a much better technology. Cool. I think we're done.